Fire melts steel. Friction vaporizes metal. And every engine humanity has ever built, from rockets to laptops, fights a single invisible enemy: heat. For 2 centuries, progress has been a wrestling match against temperature. We've built fans, fins, radiators, and liquid loops, all just to keep our machines from burning themselves alive. But what if we're fighting the wrong battle? Imagine a material that doesn't just survive heat. It refuses to get hot in the first place. A substance that takes sunlight, friction, or re-entry temperatures and quietly beams that energy back into space. No coolants, no compressors, no tricks. It sounds impossible, but researchers have already built it. In labs from Hong Kong to San Diego, scientists are creating radiative ceramics and nano-engineered composites that remain cool even under direct flame. They don't resist heat, they negotiate with it, turning thermodynamics itself into an ally. Sample tiles have survived temperatures above 2,000 degrees Celsius while staying cooler than their surroundings. Roof coatings made from the same physics have kept buildings 20 degrees Celsius below ambient, under the noon sun. If this sounds like sorcery, it's actually photon management. Engineering matter so the heat leaves as light, racing away through the atmosphere's infrared window into the cold of space. For aerospace data centers and quantum computers alike, this discovery isn't just clever, it's civilization level. Because the moment heat stops being a limit, so does every boundary of speed, computation, and flight. But how does a piece of ceramic pull off what physics says it shouldn't? How can a solid object stay cool under fire? That's where the story and the science ignite. Every great leap in technology has met the same invisible ceiling: heat. Engines, turbines, chips, rockets. Each time we reach for higher power or speed, temperature becomes the wall we crash into. Beyond that wall lies efficiency, speed, and progress. But the hotter our machines run, the faster they fail. If you've ever felt your phone heating during an AI workload or watched a launch vehicle glow red during re-entry, you've seen this universal constraint. Heat doesn't just scorch, it steals potential. A processor at 80 degrees Celsius runs slower than the same chip at 60 degrees Celsius. A hypersonic wing that hits 2,500 degrees Celsius loses its shape entirely. And keeping all this cool currently costs nearly 10% of global energy consumption. Think about that, 1/10 of human electricity just to keep our tech from cooking itself. Traditional solutions only move the heat somewhere else. Fans push it into air. Radiators send it into coolant. Data centers vent it into the night sky, trading carbon emissions for computational survival. It's an endless shuffle of thermodynamic debt. Now imagine breaking that cycle, not by moving heat, but by erasing it at the material level. Researchers have found a loophole hidden in physics: the radiative window in the Earth's atmosphere. Craft the right nanostructure, tiny pores and lattices measured in billions of meters, and heat escapes as infrared light, slipping through that window straight into the cold vacuum of space. No fuel, no moving parts, just matter cooperating with the universe. If these materials scale, entire industries transform. Aircraft that don't melt, servers that don't need chillers, buildings that cool themselves under desert sun. But breakthroughs this radical never come easy. The next challenge isn't proving it works. It's proving we can build it for the real world. Traditional materials either absorb heat or block it. These new creations do something stranger. They turn heat into light and let that light escape. Engineers call it radiative cooling. Imagine heat, not as a temperature problem, but as a stream of photons, tiny packets of infrared light. Every hot object glows in this invisible spectrum. The trick is to design materials that prefer to glow away their heat instead of holding it in. To pull that off, scientists manipulate matter at multiple scales. Picture a ceramic sponge, millions of nano-sized pores within the surface. Each pore scatters visible sunlight, reflecting 99% of it back into the sky. Sunlight can't get in, but heat from within can get out. Those same nanostructures are tuned to a narrow slice of wavelengths, the 8 to 1/3 micrometer infrared band, what physicists call the atmospheric window. In this range, Earth's air becomes transparent, meaning thermal radiation can fly straight to outer space. Pure, silent heat evacuation, no noise, no fan, no moving part. In laboratory tests, tiles made from these radiative ceramics reach temperatures 20 degrees Celsius below ambient while sitting under direct sun. That's like a rooftop that chills itself midday with zero power draw. In aerospace trials, similar nanostructured composites endured over 2,000 degrees Celsius on test stands, radiating excess energy fast enough to stay structurally stable. And here's the most astonishing twist. The same photonic designs that keep a spacecraft intact can also keep a smartphone from overheating or a quantum computer from decoring. But every new supermaterial hides a technical Achilles heel. These miracles of nanostructure aren't easy or cheap to make. So, how do we mass produce a material built, quite literally atom by atom? Here's where the science stops being abstract and starts reshaping reality. When engineers first tested these radiative ceramics and ultra-high temperature composites, the data read like an error. Tiles glowing white-hot to the eye were, by physics, cooling themselves. Sensors showed surface temperatures dropping as they radiated energy away faster than they could absorb it. They weren't breaking thermodynamics. They were finally using it properly. That single insight ignited applications across the technological spectrum. In aerospace, hafnium-based ceramics and nanostructured coatings are now being woven into hypersonic aircraft skins. Instead of ablation, materials burning away. They reuse their own heat, shifting it into light and venting it into space. A vehicle that once melted at 2,000 degrees Celsius now survives 2,800 degrees Celsius flight. Re-entry heat shield? Possibly reusable. In architecture, the same physics cools rooftops without electricity. Buildings coated in high emissivity ceramics have stayed 20 degrees Celsius below ambient temperatures at noon, reducing air conditioning demand by 30%. Cities could literally shine their heat away. In computing, nanostructured heat-radiating layers are finding their way into microchips and quantum devices, taming the thermal chaos that once throttled performance. Here's the twist. The frontier of heat control may also become the frontier of manufacturing itself. Ultra-fast, high-temperature sintering, essentially flash forging at thousands of degrees in seconds, allows these materials to be printed, coated, even 3D fabricated onto complex geometries. Advanced factories can now sculpt thermal metamaterials like artists sculpt light. The wall humanity built against heat is crumbling, not through brute cooling towers or cryogenic loops, but through a quiet alliance between matter and physics. But every new material carries a hidden test. Can it escape the lab and conquer industry? Because only then will this breakthrough stop being extraordinary science and start becoming ordinary infrastructure. Every generation of engineers eventually faces one elemental opponent, fire. For millennia, we've tried to contain it, resist it, outrun it. Now, for the first time, we're learning to partner with it. The material that stays cool under fire marks more than a scientific milestone. It's a philosophical one. These radiative ceramics and nanostructured composites don't fight the laws of thermodynamics. They dance with them. They turn heat, light, and matter into collaborators, not enemies. Picture what happens next. Hypersonic aircraft that glide home instead of burn away. Data centers that compute without cooling towers. Cities with roofs that shimmer their heat into space each afternoon. Machines that heal their own microscopic cracks as easily as skin closes a cut. That's what materials of the future truly means. Not harder metals or stronger plastics, but smarter matter. And when this revolution scales, the energy math of our planet changes. Cooling could shift from consuming 10% of global electricity to almost none. Efficiency stops being a limit. It becomes a baseline. The takeaway isn't just that we built a new material. It's that we've crossed a conceptual line, from resisting nature's forces to engineering within them. The age of cooperation between physics and design has begun, and it started with a ceramic tile quietly glowing under a blowtorch and refusing to get hot. If that's what's possible today, imagine what's next. Materials that adapt, that think, that transform in real time. Next episode, we'll step into the lab where self-healing metals are already taking shape. Materials that don't just endure stress, but learn from it. Because at Future Forge Explored, we don't just ask what materials can do. We ask what they'll become.